Yesterday it had sharing to tell season to Okay. Right. Let's start. Okay, so this is our final class. Yeah. So let's get to the final stuff. Okay. So there are two things we want to introduce today. Two more things. So one is Kunneth formula, and the other one is Poincare duality. These two things. Pick up the main stuff to talk about. We finished earlier. Okay, so one motivation question was look at this two space here, S2 cross S3 and S2 wedge S3 wedge S5. Okay, so this two space has same cell structure, cell complex. I mean, same number of cell. For example, what cell do you have in X2 cross S3 here? So on one side you have 0 cell and 2 cell, right? And then the other side you have 0 cell and 3 cell. So if you cross them together, what are the possibility you get? 0 cell, 2 cell, 3 cell, and 2 cell cross 3 cell. So you get a 5 cell. But on the other side, it's very clear that you also have 0 cell. Why is it like? How come that? Okay, let me join again. Okay, on one side, you also have 0 cell, 2 cell, 3 cell, and 5 cell, because they are wedged on the 0 cell, right? And then 0 cell come from S2, 3 cell come from S3, and 5 cell come from X5. Cool. Okay. Then you can see that their chain complex looks something like this: 0 to Z, to 0 to Z, and then to Z, to 0 to Z. So one of the non-trivial map could occur is this P map here, but this P map here should be 0. Okay, should be 0 because on the wedge side it's clear because you are not gluing 3 to S3 to S2, you just glue along the constant map. And then how about on the other side? The other side is also clear because there's no gluing from S3 to S2 as well, where we just take product. Does it make sense? There's not a tension map from the 3 cell to 2 cell. And it's just a cross product. Sorry? Both of them has the same chain. You happy with no attachment map? Huh? Yeah, no attachment map. Yeah. From the 3 cell to 2 cell. Okay. Okay. Yeah, for both cases, there's no attachment map from 3 cell to 2. So they have the same homology, same cohomology. So again, how should we differentiate them? Well, again, how should we differentiate? So we will use we will use the cohomology ring, okay, to differentiate them again. But okay, we know that the cohomology of wedge product will break up into direct sum, right? But how about the cohomology of a product space? Cohomology of a product space. So this is our main problem here. So what's the cohomology of a product space? Okay, turns out that there's a very nice property that is this cohomology will split into product as well, but it's something what we call a tensor product. Tensor product will be nicer than product. Okay, so what do I mean by nicer here? So let me define what this tensor product means. So for R modules AB, okay, we will define A cross B to be let me see, I'll try to put this. Yeah.
So
Hey. Yeah, that's right. That's right. So actually I should write like this. A cross B. Yes, quotient some relation. So what's the relation we want to quotient here? So there are few relation here. So one of them is if you tensor over R, okay, if you tensor over R, that means okay. So your R can actually move across this product. Okay, how should I write this in a better way? Should I write in this form then? If I write in this way, maybe I write this form. This is equal to RAB is equal to ARB. So I can move the scalar across. And also it is linear. So meaning A plus B, C is equal to AC plus BC. Anything else I need to take care? I think that's it, right? Huh? Is it not implied by this? Okay, sure. So A, B plus C equals to A plus A comma B plus A plus C. I think it's enough. Yeah, it is, but it's stuck. Worse than lag. Oh, okay. I think it's a line problem. So let me see. I'll connect another Wi-Fi. Yeah, bilinear. Yeah, kind of bilinear, but more than bilinear. More than bilinear. Because the R can move across. Yeah, more than bilinear. Bilinear, you just can pull the R out. But this one you can pull into different space. Yeah. Mm-hmm. Sure. R module, there's a left and right. Yeah, it could be left, right. But no matter it's left or right, right? Eh? Hmm. Yeah. Let me see what's going on here. Is it better now? What kind is it lag? I don't know people in school already. The car is not full. I think they go celebrate already. Well, let me start again. Hmm. Okay, so how you should think about tensor is a nicer thing than a direct product. Because for example, you think about R square, right? 1, 2 cannot be the same coordinate as 2, 1, right? But in tensor, they are the same. Yeah, you can move the 2 across. Okay, so you can freely move your scalar in this tensor. Hmm. Yeah. Yeah, this is the main difference with your usual product space. Huh? Original structure means what? But then yeah, sure. I mean like direct product also have original structure, right? Yeah, sure. Okay, I think you want to point out that this is another R module. Yeah, okay, this is definitely another R module. Huh? Tomorrow? It's made so. Yeah, sure. I mean, yeah, sure. Yeah, but yeah. Okay. Yeah. Any other question? Okay, so there are nice property about these things. So meaning actually this direct tensor product here will commute, also distribute. Almost works like your multiplication and addition, and it's associative. I think associative is quite clear, right? Basically, it's the same thing. And then more, I think one very important one, I guess, I need to tell you is there are more, but I picked one universal property to say. So this is a very important property of this tensor product, which has something to do with a bilinear map that Jingsen said just now. So if you have a bilinear map from A cross B to C, the real direct product, then it will induce a map from A tensor B to C as well. And I think this is unique. That's it. Okay. Yes. Which one? A tensor B. Huh? The third one? The fourth one? It's not an isomorphism. It just says that there exists a map from A cross B to C. Yeah. So how do you define this? Basically, you just take an element here. Let's denote it across A tensor with B. Send it to phi of AB. Yeah. Okay. Well, I mean, what you need to check here is you need to check that this is a module map. I think that's it. And I guess it's unique. To prove that it's unique. Okay, if you don't want to prove, you can try and remember this fact here. In future, if you come across this, it will be very useful. Any question so far? But I guess, let me see. I think we won't use these things, at least for our purpose. Yeah, I just want to tell you uh, what's the property of it. And next, we're going to define what's called a cross product. Okay, so try to put this. So, okay, here we're going to use it actually. So let us define cross product. Okay, cross product like this. Last time we have cut product, so here cross product. So what's this cross product here? So we take two elements here. We're gonna send it to something called A cross B. Okay, so what's A cross B here? Well, what we're gonna do is we're gonna define a projection map from A cross Y to X, and then Q X cross Y to Y. And then what we're gonna do is we apply P star to A, and then cut with Q star like that. Okay, does it make sense? So you have a continuous map, right? Projection is a continuous map. So induce a map on cohomology. Okay, induce a map, and then because cohomology is working backward, right? So your cohomology go from the cohomology of x to cohomology of x plus 1. Does it make sense? Your cohomology is contravariant. Okay, so go the other direction. Induce the other direction. Homology is from left to right. Homology from right to left. Okay. But then did you realize that you send it to a higher degree level because you take a P star A cup with a Q star B. You send to a higher level. This is the name of this map. So this is a cross product. Or external cup product. Okay. So this is the operation. Huh? Because defined using cup product. So that's why I call it external. Okay. So well, the nice thing about the universal property is this map will factors through this map here, going from tensor. Okay, still remember what's the difference between direct product and tensor here? We can freely move our scalar. Okay, we can freely move our scalar. Okay, turns out that this part here is an isomorphism. Okay, the first map is not an isomorphism, but when you pass through the relation of you can moving the R across, it become a isomorphism. Okay, relatively easier than direct product. Make sense? Okay, maybe you might ask, what's the ring structure on this tensor product here? Just now we just define it as a R module, right? How about ring? Can we multiply things together? So how do we multiply things together here? So the ring structure here is you take A times C cross D, you will get an alternating sign based on the element of BC here. Okay, we choose the one that is inner to this multiplication. Not A, not D, but B and C. Okay. And then we will get AC cross BD. Okay, so meaning we will multiply the contribution of the degree that gets to the other person. Why not choose AD? Maybe you can choose AD. I don't know if you can try. I think you can pick AD. Okay, but this is a ring structure that we want to put on it. Okay, so both sides will be ring. Okay, a nice exercise is this cross product here is a ring homomorphism. Maybe I just show you the calculation and then maybe you can appreciate why we define the ring structure like that. You need to understand how algebraic people do things. We set it such that things works. That's it. Okay, so we want to make things work, so we define it like that. So if you take cross product between these two elements, right? Okay, ring homomorphism meaning you apply to a product of things that is split into product. Okay, so you apply cross product to product of things, then you take the products like what we find here, and then what's cross of AC's cancel with BD is just AC cross BD by definition. But what is that? We apply the projection map to them. Okay, we apply projection to map to them, but but still remember the cup product is factorial, so we can split it up. Okay, we split it up. But then what can we continue here? Then we want to change position because we want to write it in the form of A cross B and C cross D again. But you can see that B and C, the position is swapped. So we want to swap it back. Still remember, under cup product, when you need to do the swapping, there's a graded -1 here. The graded -1 actually equals to the ring structure that we define. So that's why just now I said, can you try with AD or not? Actually, this BC here is coming from the stop of the cup. Yes. Okay. So that's why the degree of the B and C matters, not N. Okay. And then you get back this ring homomorphism. Okay. Make sense? Okay, so where's the ring structure come from? Actually come from the swap of the couple. No question? No? Okay. Yeah, very straightforward. Okay, then from here we can prove that this is isomorphism. I don't include proof here, it's in the textbook. Okay, let's see how this things works. Let's look at some examples to see how things works. Okay, let's look at one examples. Right. So go back to our motivation question there. So there are two things we had, right? What are the things we had? Let me see. No, I'm not going back to the examples. Which example I want to talk about? Okay, so I think we're gonna talk about this example. Yeah, it's the starting example. So let's figure out what's this cohomology ring here. All right. So by the theorem we had just now, this is just H star of x2 tensor with H star of S3. So maybe it's worth to ask a tensor over what ring here. So if you consider over integer, then this is tensor over integer. Okay, so on one side, we know very well what are the generators. Okay, so on one side, we know very well what are the generators. For example, the cohomology of S2 will be generated by the degree 2 and degree 0, and S3 is degree 2 and degree 3. Okay, so for degree 0 is just identity, so we don't really care much. So what's next? So then in that case, there are actually three generators here. Okay. And then this three generator actually correspond to the generator in S2 cross S3. Since they are isomorphic, we can just use the image of this cross product to be the generator. Okay. Oh, good or not? Okay. Because some you guys come late, right? So do you know how many cell here do you have X2 cross S5 here? You got a 0 cell, you got a 2 cell, you got a 3 cell, and then 2 cell cross 3 cell, you get a 5 cell. Okay, these are the generators. So these three, so maybe let me list here. This is number 1, number 2, number 3. So here is 1, 2, 3. Okay, correspond to this cell under the isomorphism. Okay, how about on the other cohomology ring? So how about on the other cohomology ring here? So H star of x2 wedge s3 wedge s5. Okay, so just now we split into direct sum, right? Let's split into direct sum. Let's talk about the reduced case first. Okay, reduced case first, only split into direct sum. Okay, so reduced case meaning we don't look at the zero, we look at the non-zero one. All right. So there are three. Each of them contain one non-trivial generators. Okay, let's call this alpha, this beta, and then this gamma. Okay, maybe let me test you. What's the degree of alpha here? What do you think? What's the non-zero? I mean, non-zero degree homology that have this generator S2. Okay, think about what's the CW complex of X2 or cell structure of X2. You use a two cell and then you bound every boundary point to a point. You get S2. So this is a degree 2 cell. Okay, so this is how you build Sn in general. You take an n cell and then you map it to a point. Is it okay? Is it okay? You think of S1. You think of S1. You take one cell and then make the boundary to and, two cell, make the boundary to a point. So it becomes a sphere. That's two. And then this is uh, in general, this is how you build Sn. Yes. Sorry? Yeah. Actually, yeah. This is the cellular structure. This is the cellular structure, cell structure. We use cellular homology to see. Okay. Okay. But then what do you see here? You can see that A cross B, right, is non-trivial. Okay. But here, if there's an isomorphism between these two ring, right, the degree 2 and degree 3 elements should get sent to the same degree 2 and degree 3. Okay. But the degree 5 here is not getting from degree 2 and degree 3. Okay. In this case here, alpha cap gamma is 0. Okay. But on the other side, A tensor 1, tensor B tensor together is non-zero. Okay. Where? Which one? Why alpha cap gamma is 0? Because there's a way to let me see. Because there's no relation between these two space. Okay, let me think how to say it. I think how to put it. Should I go this way or can I explain in different way? Because because when you do alpha cap gamma, right? These alpha cap gamma only have effects on the point of x2 and s3. Okay. Yeah, it cannot apply to x5. The degree 5 generators here applies to point on x5. Or I think in the textbook or in the lecture notes, we say that the retraction map. So another way to put this is the retraction map. I think require proof. The retraction map from x2 wedge x3 wedge s5 going to s2 wedge s3 induce the isomorphism on h2 and h3. Okay. In other words, these degree 2 generator and degree 3 generator has nothing to do with S1. Does it make sense or not? Does it make sense? Alpha comes from X2. Gamma comes from S3. S5 is another space. Do you understand? Yeah. I about you. Cycle. So yeah, I think you can hear about that. you're thinking about using the UCT, universal coefficient theorem, homomorphism from the N cohomology, the M homology. Yeah, I think you can think of that. Not detect the N cycle. Right. In this case, it's the pi cycle versus degree pi. Question? S5. S5. Yeah. Alpha is in S2, gamma is in S3, beta is in S5. Because we are not building this S5 using S4 and S3. S5 is the individual scale. Yeah. But I mean, to precisely say that is this one retraction, if you consider this retraction actually is a isomorphism. Because usually retraction just give you injection or surjection. Injection, but this is called homology. Oh, injection. I think it's injection. In homology is surjection, I think. Is it? Because P star, I star equal to identity. Homology is surjection. I think homology is injection. Yeah. But then you can actually show that in this case it's a isomorphic. R 是什么意思？哦哦，OK sure. But doesn't matter. Yeah.
打诺这人力学。
Okay. Okay. Then in that case, how about I let you guess what's this? The comoduring of X3 cross X prime cross X. What is this? What do you think? Yeah, kind of, but yeah, kind of, but we have a little bit more than that. Okay. Huh? It's actually an exterior product of A3, A5, A7. Exterior product means what? You have the graded commutative property. So many A1 cross A3 equals to minus A3 cross A. That's the extra thing you have. Okay. Yeah. You can try and calculate that, but we did it in the notes. Okay. It's not just the tensor product, it's the sorry, it's the product of, so in this case here actually is the tensor product of this thing here. Okay, so this is the tensor product that you want to see. Okay, each of them actually is a exterior algebra. Huh? No. So in general, right, if your sphere are odd degree, okay, in general, if your sphere are odd degree, actually this is isomorphic to the exterior algebra of alpha 1 up alpha n, where this alpha 1 up to alpha n is the degree ki generator, and then this degree ki are odd. Or maybe I just say this is odd, 2n plus 1 somewhere. Maybe ni depend on i. Alpha I 是啥来着 ？OK， 写给你看。So these are the generator. So okay, So the degree of alpha I should be Ki, and then alpha I will generate the cohomology ring of xki. And this okay? Yeah. Okay. All right. Every details already, right? Yeah. And maybe can greater equal 0 because maybe it's S1. Okay. So maybe I should write here that this is actually isomorphic to Z of uh, alpha I of alpha I. Let me see. Never mind. I shouldn't say. Okay. Let's keep it like this one. Hmm. So far, okay? No question? Yeah. Even. Even is a bit tricky. Even is a bit tricky, huh? Even. Uh, mm, for the even case, even case is a bit tricky. Let me see how should I put this. Even case, huh? Even case is a bit tricky. Let me see. Right. Yeah, so for even case, a bit tricky. Why? Why is it tricky? Hmm. How about even? For S2, right? Okay, for S2, um, for S2, for S2, why these two are different? For S2, do you know what's the cohomology ring of S2? Yeah. So it is generated by degree 2 generator. Okay, and then what's the relation you had there? What's the relation you had there? Actually, it's square to 0. Yeah, actually, it's square to 0. But then, but then, but then the claim here is all for all the even dimension sphere, you will just get Z alpha over alpha square. Why is it true? Okay, maybe write down the claim first. I forgot why is it true, but let's write down the claim first. So for even maybe okay, so maybe it's of S2n. This is Z alpha over alpha square. S2 I know, but why is it true for higher dimension? Eh, I'm not sure. I need to check this out actually. I need to try and check this out. Yeah. S2 is clear, but why is it X4 is true for X4 as well? I mean, yeah, let me see. Let me check first. Exterior algebra X2. What's the with this S3 and S2? Maybe I will try and write out what's the uh What's the difference between odd sphere and even sphere? Okay. Okay, so far, any other question? Maybe I can try and check this out. What's the real problem here? Any other question? No question? Okay, I'll try and fill this in. For the rest, I think similar lah. Yeah, I think similar. Any other question? Other than this one, I think I need to check. Didn't realize there are more S2N. Hello. Why you got so many back today? Yeah, I think I'm not sure this one is even correct or not. I need to check. That time, let me think. Yeah, I need to check. Check. Okay. So what I want to told you, what I want to get to you was by this Kunneth formula, right? The cohomology of a direct cohomology ring of a direct product will be split into the cohomology ring product of cohomology. Next. You might be expecting direct. No. Okay, we have something even more simple. Okay, I think other than that is not very important. Okay. You want the break or you want to just continue? You can finish earlier. You finish earlier. Seems like you still have energy. You want break or you want to continue? Break. Yeah, let's break until 3 o'clock. Yeah, 胃痛啊！哇，面包很酸哎，面包。是啊，白面包。好像生病了。
哎，我
你看到？
有那个料照，哪个把看好看的？
哦，你讲那个怎么？它不是 isomorphism 就够了。
EXMT SIM，然这个 can be realized as isomerism feature，它的 tangent bundle 和 for tangent bundle。
然后，
然如果你拿所有 different 就算你有随机派在上面有个好，它是它是 for tangent bundle 里面的控制，所以它可以。
怎么说？
反正你能直接跟他说的话，你就直接又可以直接找到那个对应的vector field。
本来不是这个意思吗？
本来我们 point wise 看它们，
慢一点，
把它领
一起看那你自己。
你的第一个 vector field。
啊。
被逼成。Homology 那边加一个 coefficient 是啥意思来着？
就是没有，就是那个你的 chain complex 用什么那个 coefficient？
哦，对，
上次有讲吗？不是，
对对
忘记 Z 模。
这边 Z 就是我们正常的。
就是谈，
你有没有什么办法很快的跟我说，跟你说的这dimension是啥意思？
等一下会讲，等一下会讲。等一下我们会 address orientation，address dimension，就是会提的，其他就一个，这两个要提一下，就是用我们 homology 的角度怎么去找它的 dimension 跟它的 orientation。有吃药吗？
说那个 line 然后来写下分以后，有没有那么好的网样？太亲切了。那因为快点有影视了。我还要先搞那个，我这太是，不想认真的做完。我跟你说一下，我在做了，我在，我还录一个，做又比较听见。
至少你的 project 都不用你 presentation，不然就要累死了。哇，太多了，一转，没有想到怎么这个做，然后3个开始到6回，8年之后那个回不来，那个方法，但是最好我就觉得是有点，我说16，然后开了多嘛，再说3个10个第3年，有没有怎么样？
哪一个？哦，我还没有去，我还没有去看。我觉得我少了好多东西啊，我要去找一下，
少了很多东西，
感觉，
我操，
因为我解释不到诶，
没有关系。
我现在其实我去看一下，我是读漏的东西。
那个，我昨天中暑，我今天才发觉，
这样发觉
我今天感觉好一点。
中暑不是会头痛还是缺水还是什么之类的？
样子，昨天很渴，
很渴啊。
然后就很累。
哦，累，疲惫。哎，你不要讲你累，我也是哦。我忽然间就情绪很 down，不知道做什么，莫名其妙啊。Happy New Year！哦，shit！Happy New Year！哦，
他这个的12，他们的这个卡的6，
什么叫卡在6？
我段，
不用交咩？7、8、9。哦，
感觉很多人都 start 在那边，这是我只做了，我开始做了。
所以 deadline 是几时？
他好像没有写，他有写，但是他
但是你没有交进，你就没有分，这样的意思啊？还是什么？
你都聊你在期末考之前
哦，你没有交就没有了。哦，
但有没有是时候？
这个有点夸张，这个不好学，这个不好学，这个不好学，这个不太好。是啊，很夸张欸，这个就不太好，都不是很好。
弟弟，我听说你还把3个 start 6本书，
哎，等一下，我们有个 quiz 啊，
讲完了咩？屌
来这个拍我一下。等一下的 quiz 是要写一下你在这个班学了什么，跟你觉得你还可以再做点什么。看一下你们一开始写的东西。
我学到不应该拿这个课。OK，
做到直白吗？
说这个
你才学到，
太难了，
你才学到，
我早就学到了，你们看我的。
那你怎么还继续
对啊，怎么来拿这个课？我就很好奇，你干嘛来拿这个课
因为写很多课没知道。
？Finance 啊，你要故意来拿呀？对呀，你就过来拿，你来骂我，我打你了。
百年蠢啊！没有太
过分了，
你拿过
才百里
啊？
百
年以上
嘛？
哦，那你还写我的课拿什么？
好的，真好。昨天真是第一个我会的，
我不知道，我不懂。
店在哪里？
我都弄偷不到，偷不到。
免得都不去做。
他可以来吧？
你们
你又怎么又不关注你的？
没关系，如果咱后面有可能是你懂吗？哦，这个就是给他绑架。
等下你们写的东西不是之后我们会把它放在那个 lecture 吗？
啊，
所以写好一点。
啊，哪
没有啦，不是写好一点啦，就是写
这个写
比较那个 make sense 的东西。
意思你要放这儿，
什么
放这儿？
什么叫放这儿？
这个来之后
哦，每个人就是任何的得到的东西还可以做更多。然后我再 brief 你们，我只是派回去给你们，
让我学好。然后 A
等你写在里面。
是一个很强的电脑，
你写在电脑，
什么叫是旁边吗？
那去拍一个，这里。
不是，
先不要写啊，先不要写啊，你先想先。
多的
先不要
我
写啊，
这种也是会帮你。
那个不会了，因为我要做那种前沿的东西。OK 啊，
多的只给我是吗？
等下我再 brief 你们写什么，只是说让你回味一下你的 week one，现在是 last week 了。这不用，这要咩？这想写咩？他有什么感触就这样写了 ，as a observer。
observer，我现在知道没有哎，
什么？
上了我
嗯哼，
我真心觉得 API 是为了其他人而创造出来的。
多的只给我，
对其他的，
不是我，
你喜欢的，你要
对对对。
它是一个很强的工具，
很强的东西，
非常强的。
非常强的东西。
可是它本身的话是有点软。
OK， 如果你觉得它很强，不是你再读多一点，还有更强的东西。等下做 quiz，等一下再讲，先给你们先，等下再讲。OK，right， so 重头戏啊 ，this is the most important thing of this algebraic topology course. Okay, this is the most important thing, but we won't test on it. The most important thing, which is the Poincare duality. Duality theorem in mathematics is very strong actually. All the duality you can see whatever dual you see. Okay, but this one is a Poincare duality here. So the easiest case is for compact manifold, compact, connected, close, oriented, everything very nice of dimension n. This n is very important. This n is determining how we find this duality. So we have a duality isomorphism between homology and cohomology. It's not between I and I, instead it's between I and n minus I. So it's like palindromic. We have palindromic. 解释一下 Rachel. Give me a palindromic word. Word 有吗？应该有，不是？
有
palindromic word Larry 也可以。Mums is a palindromic， 知道什么意思吗？正正念、反正念都是 mum。palindromic。OK， 就是有一个 symmetry along 那个中间 ，along the center character level， 反正念、正正念 level。OK，palindromic， 这个 I and n minus one is the same。 Okay, palindromic phrase. Okay. 山海自来水，
海上
来自来。Okay. Sure. Okay. Cool. Good. Right. So the corollary here is we can link this cohomology back to the home from homology out of homology. Yeah. Then this will be a bilinear pairing. So in mathematics, this kind of bilinear pairing is very ubiquitous, right? We have seen a lot, right? Yeah. So between homes, between the dual and the vector space, you can form a bilinear pairing. A bilinear pairing will give you an isomorphism, and isomorphism will give you a bilinear pairing. Okay, and then this will also imply that their complementary Bernoulli number is the same. Need to prove that, okay? But then I just want you to observe these things first. Yeah, need to prove, but then as an application, right? Combinatorics application, we can use the homology or the cohomology of a n torus. N torus here meaning you cross S1 n times, and then you will get this your high school formula n choose k equals to n choose n minus k. I think the non-trivial thing, okay, obviously point product duality is very non-trivial, but once you have point product duality, next thing I think you need to figure out what's the homology and the cohomology of it. And these will give you the right number. Okay. So in this case, right, it actually suggests that a lot of combinatorics problems, right, maybe come from geometry. Or you can use geometry to solve combinatorics. Okay, it's not just arithmetic miracle. It's not just the arithmetic miracle. Maybe you can use the tedious combinatorics way to compute, but you can have a nice space to realize it. Or sometimes the space is very complicated. You can be reduced down to just a combinatorics problem. Okay, so see which side is easier to solve. Okay, mathematics is always use things like this, right? Because like as you see, Gödel's incompleteness theorem, right? So in one side, you always have something you cannot solve one. So you need a new problem, new theory to help you to solve it. And then the new theory must have something that it cannot solve one. So you need another theory to solve it. So you can get a look. Yeah, so the research work, you always has demand for research work. Gödel's incompleteness. Thanks to Gödel. 什么？对，
拿一个跳人出来。
你解释给他听。Gödel's incompleteness. Okay. So okay, now we will make precise what is manifold. Okay, what is dimension of the manifold? What's orientation means? Okay, using homology. So what's manifold here? See whether is this manifold same as your manifold or not. I mean, in the differentiable manifold case. So the manifold we consider here are Hausdorff space, meaning you can separate 2 points using 2 open set, right? I still remember. And for every point in X, there's a neighborhood UX homomorphic to Rn. Just homomorphic. We don't need differomorphic here. Mine stronger, me? Weaker. I don't know. Yeah, weaker. Okay, so so the remark here is the dimension of M actually is intrinsically characterized by the fact of your local homology group. Okay, so why is it true? If you look at this local homology group, if you still remember, it's the relative cohomology by comparing to the complement of a point. Okay, you can try and reduce this thing here using addition, meaning instead of looking at the whole M, you just look at the smaller open set around X. Okay. And then because this open set will be isomorphic to Rn, then you make it to Rn again. Okay, so why is it looking at Rn? Because Rn is contractible, so it's nice. We can work out things. Okay. So in that case, we just reduce to the reduced homology of this complement of 0. If you look at the long exact sequence of the pair, because it's computable, right? A lot of place is just 0, 0, 0, 0, 0. Okay, so the relative homology is isomorphic to the space you quotient on, the chain subspace you quotient on. But then I think we know what is Rn cross. I think Rn cross point, right, is Sn. Sn we know very well what is the homology. Homology? Yeah. Okay, so you only have non-zero homology at I equals to N. Okay, good. Makes sense? Okay, so this is one way how we define the dimension of a manifold. Okay, by using the local homology group. By using the Does it make sense? Does it make sense? I mean, in the differential manifold way, you would think that, for example, why a sphere is a surface? Because you can use R2 to patch around the open set. You have a charge. So here we consider the local homology group on the sphere. But this sphere is like lower degree down, but then your homology also lower 1 degree because of the long exact sequence. So it turns out to appear at the right spot. Okay, make sense? Make sense, man? Okay. All right. So meaning we define the dimension of a manifold to be the only non-vanishing degree of the local homology group of M. Because we can always reduce it to the reduced homology of a sphere. Okay, then what's the orientation here? Also, we're going to use relative homology to tell you. Because we know that local homology group is always Z, right? The non-zero part is always Z. Then Z has 2 generators. So you tell me which is the generators? This will be the orientation, local orientation, locally. Okay, for example, on the line, how many orientation you can put? You can go left or go right. On the surface, clockwise or anti-clockwise. And 3D, left hand rule or right hand rule. Yeah, no. So these are usually because Z only got 2 generators. Okay. Yeah. Okay, so now you can relate your orientation to Z. But then if you have this local orientation, right, basically it will determine all the other nearby points, the local orientation at the nearby points. Okay, because you can make your relative homology bigger a bit and then split it to another point. Then they will have the same. They will have the same generator. I mean isomorphic generator. Okay. Using deformation retract. Okay, so now we're going to define what's a global orientation means. So meaning the orientation at every point. So this is a continuous choice of local orientation. So make sure your choice is continuous with respect to this method. So every point you have to choose the generator, every point to the generator, and then make sure that this map is continuous. And then satisfy some local consistency formula. So what's this formula here? I mean condition. So for every x in M, there exists an open ball of finite radius and x, and a generating class of hash n of M, comma M slash B. So what's this MM slash B here? So let me see. So this B here should contain the point X as well. Okay, contain the point X. And then this large group, this large class here should restrict to the other local orientation inside that four. Does it make sense? Does it make sense? So on one point, right, you have mu x. Every point, every x you have a mu x. Okay. And then if you look at a certain x, you have a ball around it. Right. So around it should have other x's, right? Let's call it y. But then you also can cycle from this relative homology, right? This m comma n slash b. Okay. Then you can restrict this class to point. Correct? Is it true? Correct. Restrict this mu b, the class of mu b, to the class of mu 1. Okay, they have to be the same. And only then this local consistency will work. Okay. Make sense? Does it make sense? 原题吗？可以问的，不用紧。Okay. Does it make sense? Yeah. So after your restriction to this relative, is it relative? Because m slash b is something larger, right? And then you portion it. And then this one m slash m slash y is larger because y is just 1 point. And then the element in cm cross cm slash b, sorry, is in the chain group of m slash chain group of m slash y. Sure. So if an orientation exists for m, then m is co-orientable. Yeah. Any question on this definition here, orientation? So the orientation we talk about in your first year or what, those are global orientation. So meaning if I go left, then everything go left. Okay. So maybe one thing I want you to get out from here is the orientation we pick are the generator inside the local homology group. Okay, our local homology group is just Z. So there are only two choices you want to pick. Random. 1 or minus 1. You can choose 2, huh? Cannot generate. Okay, 1 or minus 1. Or depends, actually, if you change to different coefficient, maybe you have different story. Okay, if you change to different coefficient. But here we consider Z first. Yeah. Yeah, yes. So maybe that's not the usual geometry you see already. Okay, yeah. So for now, what you see is exact. Okay, so the theorem here is we can always find something called a fundamental class or orientation class. Okay. So if M is compact oriented, then you can actually find this class here, this homology class. This homology class, actually, you don't find it inside local homology. You just find it in the homology. So the top homology. You just realize this is the top homology because you have dimension 10. You go to the top homology. Okay, to find it. Did you guys touch the ram in differential manifold? Huh? No. Your top, your volume form. Volume form. Okay, volume form is something living in the top to the ram homology. It's dimension 1. Your top homology is always dimension 1. Okay, because you cannot wedge anymore. If you wedge more, you go 0 already. Okay, n form on, yeah. So in this case, you can think of this n form here actually. I think this This fundamental class corresponds to the volume form, the end form, the top form. But we don't prove it. Okay, so to tell you about the Poincare duality, right, the isomorphism, right, we need to define one more product called the cat product. Finally here, cat product. So what's cat product doing? You take a chain group and a co-chain group together, you get a chain group. So we need to check that this induced maps on homology and cohomology, such that we can get homology cross cohomology, get a topology like that. Okay, make sense? Make sense? Yeah. Okay. Can you imagine how we're going to use this thing to show the isomorphism? Can you imagine? Just now we have I and n minus I, right? So here got k and k minus l, right? Okay. So the I will appear on the homology side, and then the k will be fixed to be an n. So there's a n homology that we care about. But just now I tell you there's some n homology very important. So we're going to use the fundamental class to build this isomorphism. Okay? Is it okay? We take a fundamental class, cross with a cohomology, get you to the homology, n minus e. Yeah. Okay? Okay. Okay. So basically, how to prove that this. Okay, so what's the definition here? This definition here very cute actually. Very cute. You see that this is very cute. Because what do? You kind of let this cohomology, add on this homology. But maybe because your cohomology is smaller than your homology, right? You only can add the first few of them. But what's the rest then? So you just evaluate the first few, the rest just stand as what it is. 很勉强，我已经 add 不到你了，把你放到边，就这样。OK， 但是好用，很奇怪。OK， so you just evaluate your simplex acting on the first few faces, first few vertex, not vertex, sub-simplex. Okay, turns out that there's a induced cat product on the homology and cohomology, so you need to have this kind of likeness rule again, like last time. You remember when we proved that cat product induced map on homology, so you also have a likeness rule. So here also the likeness rule, very interesting. 一边是红，一边是圈，一边是口圈，还有这种likeness rule 在。Okay, very interesting. But to prove this is just calculate what things get cancelled. That's it. Okay, make sure if you want, you just make sure that you know what to cancel. And we also have this cut product between relative and absolute homology or cohomology. Okay, yeah, very similar to cut product. And then a very different thing about this cat product is this natural reality. So this natural reality here, if you look at this commutative diagram, this diagram here works different way. It's like a highway here. Highway. One up, one down. Okay. So if you have an induced F on your homology, your cycle, and then a cat with co-cycle, actually it's equals to acting on your co-cycle first, and then cat together, and then add by your F again. So what's the direction here? Maybe we can draw this direction. So you do your F star and then you cat is equivalent to you go up here and then go down here. Like that. Okay. Or maybe I should say take identity, and take identity. And then this one identity on the other side. Okay, make sense? So you go up and go down with a different map. So one map you take F star tensor identity. I say tensor. This is not tensor. Maybe just take a cross. Yeah, just take a cross. It's like the matrix. 2x1 matrix. 2x2 matrix. It's a 2x2 matrix. On the diagonal side. Okay. Okay. Then we will have this Poincare duality. This is Poincare duality by using the fundamental class here. So you have a homology, and then you take the cut product between homology with fundamental class, which is a homology, then you get a homology. Then you get this is a homology in n minus c. Okay, so let you see an example. So what did you expect here? What did you expect this map is? Because HK are modules and they are finitely created, or they actually have finite bases. So supposingly, this map is a matrix. This is a matrix, just the matrix. Later I'll show you what type of matrix you get. And moreover, you expect this matrix to be invertible because it's the isomorphism. Yeah, actually, linear. Yeah, cut product is linear. Okay, yeah. Okay, yeah. So this things here is a matrix. Is a matrix. Okay, so if you look at this example here, torus example. Okay, I think you see the CW complex plenty times already. But now we're gonna introduce this two dotted line. Sometimes we call it a dual cell, but for now, why we draw like this? Do you have any idea? Okay. Why do we draw like this? Okay, so it's if you intersect some line, then intersect the line that we cross, it will take one at that line. It will evaluate one at that line. Does it make sense? For example, if you look at the white line there, right? So phi applied to A is 1, but phi applied to B is 0 because it doesn't cross it. Okay, so this is how we draw them. Does it make sense? Okay, so if it crosses it, then we will evaluate that one simplex to 1. Okay. Okay. Right, so if you notice, so what we're gonna compute is they are actually co-cycle in H1. So why is it a co-cycle? So basically, you just compute. So you compute, for example, what is delta phi on sigma 2 here. So these are the two cells. Okay. And then you check that actually it maps to 0. Okay. Moreover, using this definition, right, you can see that purposely I miss B for phi. I miss A for psi. Okay. So actually they are dual to this cycle here. Okay, A and B, they are dual to it. Okay, they are dual to it. Okay. And then what else we need to know? So did you realize that our two cycle actually is these phases, sigma 4, sigma plus sigma 3 minus sigma 2 minus sigma 1. Okay, so maybe have a look here. Sigma 4, and then sigma 3, and then sigma minus sigma 1, and then minus sigma 2. Like that. Okay. Okay. So why? Basically, you just compute the boundary. such that they cancel out. Okay. Okay, so why are we caring about these things? So are we set to compute the Poincare map already? Not yet. But what we're gonna do is, let's see. Oh, so if you kept these two together, I think last time we showed it already, right? If you take the two generators, one degree one generators kept together, we will get the degree two generators. But in this case here, what's the degree two generators here? You actually kept these two together. Okay, kept these two together. And then you check that actually this is the dual generator to the the two cycle we found. C here. Because it had the value 1 at there. Oh my so that's fine. Okay. Then we will choose this C as our fundamental class. Okay, because it's a generator. Yeah. Okay, if you cannot follow, you just think of this C as our fundamental class because this is the generator in the top form. Okay, we can choose it as the fundamental. Okay, so we'll take this fundamental class kept with the degree 1 elements. Okay, so degree 1 elements. For example, this phi and psi here. Okay, so how do we do it? Still remember how do we do it? Okay, we will take this fundamental class and then kept with phi. So how do we do it? Still remember or not? Still remember the formula? We only have one simplex to apply with this phi, right? Because this phi apply on one simplex. Okay, so you can only apply on the first part of sigma 4, first part of sigma 3, first part of sigma 2, first part of sigma 1. Okay, so if you go back to the picture, first part of sigma 4 actually is E1. You have to verify it. Maybe let's verify a few to convince you. So if you look at sigma 4, right? So where's the direction? Here, 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 right? Okay, so the first part is E1, second part is B. Okay, so actually you only add on the first part. Okay, take your phi, add on the first part, E1 only, and then multiply by your simplex restricted to the second part. So you do the same for the rest. Okay, then what's left is just minus B. So meaning what? You send phi to minus B. And still remember what this phi is? This phi actually is a dual to A. Phi is dual to A. A 我是不是写反？哦，没有写反。我写反了吗？我有东西写错。Let me see. Okay, I think this is A. Okay, so you can see that phi is something that dual to A, but under this cap product, it gets sent to minus B. Okay. If you compute, how about cap product with phi? Okay, do the same thing. You apply your psi to the first part of your two cell, and then the other part of your two cell, you just multiply with it. So you get A. So if you write down what is H1, what is the first homology, what is the first homology, then write down the basis. Okay, write down basis. So maybe, can I write down the basis here? So let's write down the basis. So maybe this part is A, B, no, this part is phi and psi, right? And then this part is AB. Okay, so what happened just now? We send phi to minus B. So this will send phi to minus B, and then this will send psi gets sent to A. Is this true? If you cannot see this basis, I think we need to do a change of basis here. But change of basis here is just making it into the standard basis, 1, 0, and 0, 1, like that. Okay. Okay. Any question? So this is an isomorphism, but not an identity map. Yeah, even if you swap the order, you still have a minus sign. What do you think? What do you think? Any question? Sorry? Oh, I mean like if you want to swap, you want to change the basis, right? Instead of AB, maybe you become BA. Then your matrix will become 1, 0, 0, minus 1. It's not an identity, there's a negative thing. Okay. So far, okay? Yeah. Okay. Then you can see others examples. For example, this one here. What's this map? This one is an identity map. So in this case, this one is an identity map because H1, I think there's only one element inside there. Okay, you send the U plus L call cycle to A plus B cycle. In this case, it's an isomorphic, it's an identity map. You see non-trivial matrix here because these H1 are either cohomology or homology. They are two-dimensional. Okay, you still remember. Is it true? First homology of torus. Is it two-dimensional? Yeah. So that's why this isomorphism is a 2x2 matrix. But if you look at the RP2 case, the H1 here is just Z2. Okay, so it's an isomorphism. Actually, it's an identity. In textbook, I think they do for higher genus. Okay, so far, any question? Any question? Can you see the isomorphism through this torus case in H1? Can see or not? Can see? Can understand this matrix here? Okay. Huh? Okay. Yeah. Basically, this matrix here is this cut product. So this map is the class cap with something, cap with things in the first column. Okay, because it's a linear map, linear transformation between finite dimensional space. So it is a matrix transformation. Okay. Yeah. Okay. Yeah. Okay. But we also have Poincare duality for non-compact stuff. Okay, but for non-compact stuff, we only have statement for compact supported core chain. Okay, only for core chain that is if you have a compact subspace of X such that it is zero away from this compact set. This is what compact support is. You are supported on the compact set. Other than the compact set, you are zero, man. Okay, so for non-compact manifold, we also have Poincare duality, but only for the cohomology of compactly supported cohomology. Okay. So I won't define the map for you, but I just want to give you some ideas. There's a lot more algebra you need to learn to appreciate this. For example, what's the limit of what's G alpha here? Limit of subgroup. Not epsilon delta. It's just a bunch of direct sum. Yeah, it is the direct limit. It is the direct limit. Okay, not the epsilon delta limit. Okay, it's a direct limit. You need some diagram to do it. It's about universal property. and mapping into a diagram, mapping out from the diagram. I won't tell you what's exactly, but just give you some ideas that this kind of thing exists. And the nice thing about the cohomology of compact support is we can realize it as direct sum of some relative homology. This thing you know, this thing you don't quite know. This thing is just not what we do. So basically, you need to take a bunch of this. You see, this K choose in I, so there's a bunch of compact set you need to consider. Okay, a bunch of relative homology. It's like you need to consider all the possibilities. Right? All the possibilities. So let's say you know how to compute relative homology on this compact set. How about this one? Are they the same or not? Okay, so this is the idea of direct sum. I want to consider all the possibilities. The idea of it. How to consider all the possibility of doing it. Okay, so next time if you think of this kind of idea, maybe you can come back and look at this direct sum. Okay, you want to look at all the possibility and mapping in or out. This cohomology with compact support is very interesting because if you compute it on Rn, right, you can see that there's a non-trivial cohomology existing there. Because last time we always say that Rn is contractible, the cohomology of Rn have to be the same as the point. But if you just consider compactly supported cohomology, there's a non-trivial Z coming out. There's one bad thing about this construction is that this is not an invariant of your space because your space is contractible, but you still have non-zero thing. Okay, but it is detecting something else. Okay? This completely supported core chain, right? Core chain that define this. Then what's the statement here? Maybe I just go straight away to the statement of for the non-compact manifold here. Then you will have duality between H n minus k homology with the compactly supported K cohomology. That's it. Okay, you only have compactly supported cohomology that has duality. Okay. Yeah. And then any other corollary is you can see that first corollary I think is very useful in even in your differential manifold. If you look at the top top cohomology is just R itself with one dimensional. Okay, one dimensional. I think one dimensional is the most important thing part. Right. For example, I mean like you integrate a line, right? Dx. Did you see other dx or not? Or can you do dx slash dy in first year or not? So there's only one dx you need to consider in real life. Okay, in the calculus 2, dx dy. Surface dx dy. No, you didn't see dx, right? You didn't see dy, oh? Huh? They are 0, correct. Okay, after you learn all this, you know that those things are 0. There's no dx 啊，怎么没有教 dx 的？怎么只教 dx dy？ Okay, yeah. Okay. So there's really only one thing you need to consider there. It's one dimension. And then the next corollary actually very interesting. If it's an odd dimension closed manifold, actually all characteristic is 0. Very interesting proof. This one you can have a look. So I think something to do with palindromic that cancel out. Very interesting. That's proof. And what else? Okay, so for closed-oriented connected n manifold, the torsion of Hn-1 m is 0, also using universal coefficient theorem. So meaning there's no torsion inside the homology below the top homology. You might think, why is it n-1? Your universal coefficient theorem relates the n homology with the x of n minus 1 homology. So that's why you can only talk about the torsion and the lower homology. Okay. Yeah, very interesting. And then final menu. Okay, done. This one is the last one. Okay, so what should we do first? Do quiz first? 除了 quiz 还有 exam tips，还有拍照，都哪一个先？啊，还有12分钟，来得及，来得及，很快啊！还是讲 final 先，讲 final 先啊，你心情会比较好一点。Okay, so 我们讲 final 先。Okay, final. So okay, so please learn Euclidean neighborhood of the topics while the topology is defined individually. 看得懂我在写吗？So 就是so what I will specify some topics, and these terms you have to be very familiar with them, and then try to make connection with them, find the hidden layer. I don't know what neural network you're gonna use, but this depends on person. Okay, so this topology you find individually. So, ？OK，可以吗？可以吗？因为我不知道你的内部部要学多大，对，这是 depend on 你的 topology。如果你觉得你要学多一点，就要学多一点。你觉得你学是哦 ？Obviously, but you can reduce, right? Okay, so first part is dealing with topology and homological algebra. I think this is the most true question. So about homotopy equivalence, homology, how they're related, relative homology, how these related to contractible, and then reduced homology, exactness, and equivalence. So maybe you might think of in sequence, actually, at least in sequence. So maybe you can think that how is this homotopy equivalence affecting homology, like that, right? So how contractible will affecting relative homology, and then how reduced homology will, have connection with the other things, and then exactness and co-kernel, how they connect. But these terms, I think you need to familiarize first. I would say that the question are mostly from nationals. Okay, let's go through first. Let's see how it goes, then we can comment more. So how about for homology part? I think most part is homology. Okay, most part is homology. So you have to know very well how to compute the homology of torus using either simplicial, singular homology, whatever. And then RPN. Okay, RPN, I have a specification here. You need to use cellular homology. Okay, so make sure. Yes. If you want to use cellular, also can. You have to use Mayer Victorious 也可以。什么叫写答案？要有步骤啊，不对？对，要有步骤。So I mean like torus, if you want to use Mayer Victorious also can, you want to use excision also can, whatever. But yeah. And then the other thing is about Mayer Victorious one as a sequence. Okay, I want you to talk about the connecting homomorphism there. Yes, diagram chasing, must have. This is a must have in this course, diagram chase. Okay. Okay, so one last question is cup products. Okay, we want to show that two spaces are not homotopy equivalent using cup product. So try and familiarize with the examples. That's it. I think around 6-5. Homology, yeah, cup product. That's it. To show that two spaces are not homotopy equivalent. Very similar to lectures problem. Okay, so basically you need to identify what are their homology ring, and then why their degree, the corresponding degree generators after they multiply, one of them is non-zero, one of them is zero. You need to explain why. Okay. Any question on this? 没有啊，那是 about homology 吧？这没有 Victorious is about homology 的。之前 没有那个没有。Comoji I just test on cut product. For Comoji's chapter I just test on cut product. That's it. 对，你应该要 spend more 一点 time 在 Comoji。你要的话，for Comoji 你只要记得他们的 Comoji ring 就好。我应该没有叫你真 Comoji ring 是什么。
记得
For example 我会给 ，for example RPN 啊、CPN 啊这些不会给，还有 S2 的啊、SN 啊这些基本的。
link structure
还有什么呀
link line
？RP 呀，
不是我鸟
不，是，
你脑袋都坏掉了。
没有，就是 like cut product 就是基本的那些 RPN 的、SN 的 Comoji ring 你都要知道。我不会叫你 prove，but 你要会用啊。然后这里考的 Comoji 会考的部分只是考你知不知道这个 degree 乘起来过后为什么是零，然后为什么在另外一个地方不是零，这样子还记得吗？我们 isomorphic 过去，然后一边乘起来是零，一边乘起来不是零，所以他们没有 isomorphic。那些 ring 你要记得一下，我没有给你。Maya Victorious 我会教你怎么去猜那个space，但是我也没有给你。OK，说我的 OK，讲到这样子的话，就是说 homology and cohomology of RPN、XN 这些全部你都要很熟，基本的都要很熟。OK，for homology 我会叫你修，for cohomology 我不会叫你修，我叫你问吧。可以用 OK 吗？对不对吗？说简而言之，你的 homology 跟 homology of RPN 啊、SN 啊、这种 CPN 啊这种，比较很熟呀。好人说，这种基本的 space 你都要很熟。homology 我会教你读 homology 我教你用吧。OK，没问题吗？没问题。OK，说做 quiz。write down what you write down。哦，还有一个东西是，那金生问我，读完这个课过后还有东西好读吗？还有好多东西要读，超级多东西要读。So you can go deeper in homological algebra or even 你有提到嘛 representation theory basically 就是 module theory 啊。representation theory 有分 like representation for algebra for groups finite groups for D algebra D algebra 小叶在读的 D algebra representation of D algebra and then 我们可以更 abstract 哦，进到 category theory 哦。or even 我们可以 go to infinity category 在 infinity category 我们会学到有的 something like the 而且还是我记把 one of the is nerve 有点像把油的词，因为就是一整串东西 spine is fine 嘛，好像有 spine 好像有 you can have a look and then next part 是 homotopy theory 嘛，上次我们讲过了，但是I think it's not enough to just learn the homotopy theory inside the actual algebraic topology textbook because actually you need something else to help you like stable homotopy theory or the K theory like the bundle. I think vector bundle is what you agree on. Oh, okay. And then more to that, you can go to a differential topology. So you combine differentiable manifold with topology. And symplectic geometry, you can okay, so symplectic geometry actually is the mother of all maths. Basically, you have to learn everything to appreciate this subject. And then you can go to algebraic geometry where you can consider like the shift homology. And then you will see a lot of direct limit there also. The limit you will see. This is what all the mathematicians say. To learn symplectic geometry, you need to do every math. Every branch of maths you should do. You need to learn everything. Every two equation. Because there you also have 10 complexes. Then you also can do analysis.
You
Everything you can do there. Yeah, you can do everything there.
cannot.
What do you mean? I mean, like, obviously it's stressful, but you can do everything there. Okay, so 5 minutes, huh? Okay, so write down. I think I can borrow 5 minutes. 跟那个老师讲的，我们拍照可以出去拍的。So write down what you gain from the class, and then what is your how should I say 感触的英文是什么？啊？Thoughts 咩？Thoughts 太简单了。What's your
aftermath feeling?
aftermath to English? What's your feeling? What's your thoughts? What's your feeling? What's your feeling after? 很奇怪哦 feeling. But anyway, after the course, then
Thinking from this kind.
Yeah.
Brain dead.
okay, I think these two things.
Feeling after the call. Particular.
那老师你在这个在补看，
这要写分级，
Luck.
不用，会几个在？哎，为什么产品在这边呢？
他刚学完 LA，
哦，OK， Yeah,
现在 gay
yeah，
不是这个。
写一下，给5分钟，看他们老师来了。Maybe in your point you can record like how they change your view towards mathematics. Along this line is fine. Maybe 1 more minute. 1 minute.